Hey everybody, this is Larry. This is me going with Q3 of the bi-weekly contest 163, minimum cost pass with edge reversals. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. This one I solved in about, 4 minutes? And honestly, because it is, I want to say a straightforward problem because it is just a lot of theory, right? But once it's a good test of your understanding of the Dijkstra's algorithm, or shortest path, or greedy, one of those things, or maybe all of those things in a way, right? And the way to think about it, the way that I thought about it in any case, maybe it's not the only way, whatever, but the way that I thought about it is that, okay, so you have, some nodes, this is directed, of course, right? This is directed, whatever, right? And it may even go the other way, whatever, yeah, I don't know, right? Like maybe this here, right? And you're trying to go from, say, a node to here, right? The idea about Dijkstra and greedy, and of course this assumes that all the weights are positive, otherwise you're going to just have a bad time, is that when you get to a node in a greedy way, the part that you have to understand in the greedy way of Dijkstra is that when you add a node, this is the earliest time you can do it, right? Earliest time, right? This is why I don't write that much. The handwriting is terrible. Yeah, but yeah, this is the earliest time you could get it. So what does that mean for this problem, right? Okay, this is greedy. This idea of optimality with respect to the previous states, etc., right? But yeah, what does that mean? That means that when you go to here and assuming that you do the weight, you do the math, and you relax future nodes, every node you say this is true, right? So that if you process this one next, this is the earliest you can get it. Well, what does that mean for edges? That means that now, well, there are two things. One is that if this is the earliest you can go here of all the possible paths, that's how Dijkstra, that is everything on Dijkstra is built on that greedy assumption. That means that another way of saying is you will never come back, right? Meaning that once you're in this node, you will never go back to it, right? So what does that mean? That means that to kind of let's look at, I don't know, an edge, right? For example, this edge, if we want to reverse it, oh no, the other way, maybe this is it. All right, let's look at another node. Let's look at this node, right? Okay, let's look at this node for now, right? And let's say you want to consider this edge, and you want to consider reversing it, and you're here, and here means that this is the earliest time you can go to, right? If you do the Dijkstra calculation of the time you could get to this node plus the rate of reversing it, which is 2 times W in this problem, is greater than if it's less than here, if that allows you to get to this node the earliest, and we haven't visited yet, because if we visited, then we would have already visited, and also greedy, positive numbers, etc. That means that, well, one is that we never come back anyway, so that means that if we reverse the edge and we go here, we only do it once, right? And why? What I mean by only do it once, that means that if you want to try, in this node, let's say you have multiple out edges, so you have to consider, let me change the color again. You're considering reversing this one, and this one. But keeping in mind that in the shortest path scenario, again, I'm repeating myself, but I just want to, is that you can only leave it once. You will never come back. So that means that if you're considering all these things, and one of them will get you the shortest path, it's fine, because you will never come back. Meaning that the constraint of you can only flip one of them, you'll never violate it, because you never come back to have a chance to violate it, right? Because you can like go here and then another way, I don't know, come back this way, come back here, and then do this way to make it go twice, right? This cycle will never give you a shorter path, right? So that's the core idea behind this problem. And once you realize that, then it is honestly, literally, just straight up Dijkstra's algorithm. I'm going to highlight, most of this code is, like I said, like straight Dijkstra. only thing that's different is this one line of code, right? The only thing that's different, this is regular directed Dijkstra, except for this line of code, and that's it. I mean, we can go over it. I'll go over it for the next minute just because we can, and it'll just be a minute because it's Dijkstra. If you don't know Dijkstra, definitely study up on it, right? Obviously by now. This is not a, I mean, I would say this is not a beginner's video per se, but I mean it is, but also like you should just have it. Like you need to study it, it's fine. There are a billion videos on Dijkstra's algorithm. You don't need to come here for a one-stop shop. Watch it, come back if you will, right? And then watch it again. Drive up my view counts. No, but yeah. But yeah, everything else is standard Dijkstra, right? Edged list, construct in a directed way without this idea of reversing. You would just maybe only have one direction. That's how you do directed, right? Set up the best. Use a heap on a Dijkstra heap. Give it a node. Make sure you haven't visited this node before. Oh no, this is sorry. This is the return one. You know, if we're at the end, return it. If we haven't visited, if we already visited this node before, we skip. Otherwise, we visit this node. We look at all the edges, and this includes the edges in which back edges, right? Because we just calculated a different thing. It includes the edges in which reverse. If it is the best way to go, it doesn't matter if it's reverse or not. We just update it, can put it in the priority queue to go, and then do it all over again in the while loop. If you cannot reach to the end, meaning that this never gets hit and all the heaps are done, then you just return -1. You're a little bit sad boy. Yeah, and that's it. Like I said, everything, I'm not going in detail because this for me is standard Dijkstra. Maybe your implementation is a little bit different, but this is standard Dijkstra, right? This line of code, that's it. That's how I'm able to get it in 4 minutes, right? And probably even a little bit slower in there. I mean, some of it is like me proving it in my head or whatever, but yeah. This is standard Dijkstra complexity. Again, this is going to be V log Y. V is the number of vertex, Y is the number of edges. Or you could say 2 times Y because whatever, but in the log it goes away. And you could reduce this to V log V with a better heap implementation, but it's not worth it generally. Because log Y is only 2 times more than log V, right? You can prove that at home. And that's it. That's what I have for this one. Let me know what you think. Thanks for watching. And yeah, you could watch me solve it live next, and it's very quick anyway, so watch it. But okay. That was a tough one for me anyway. I don't know how other people did it. I should have done that earlier, visualization. I was talking about it, but I didn't know how to do it. What time is it? Man, 25 minutes for that one, or 20 something minutes on that one. All right, focus. Let's go. We got it. All right, weight edges, direct edge. Okay, we have a directed weighted graph. Each node has a switch that can be used at most one. I'm not use the switch when reverse. You may activate incoming edges and reverse the, and each node can only do it once. I mean, it's just regular Dijkstra, right? Let's see. If you reverse an edge, basically, I mean, it doesn't matter. You will never come back because you're already at Dijkstra. So it's Dijkstra, right? And that's negative. Wait, no. So it's just regular Dijkstra. Okay. This is actually way, to me, easier than the other one, just because it is. Like easier than Q2 just because it is standard theory, right? And I say that, I don't know, I've been watching a lot of chess, so I feel like I'm like using the chess language a little bit. Okay, yeah, where am I going? From 0 to node -1, so yeah. What am I doing? How am I so bad at this? I am rusty, as you can see, because I should not hesitate on how to write Dijkstra, but it is what it is. I think that's all I need, though. Yeah. distance node equal to. I am very rusty. Like I feel like this is automatic. If otherwise. All right. And technically speaking, even if it is T, no, it should be fine. Okay, focus for W in. I mean, we have to make modifications. I'm going to make the modifications soon, but for now, let's do this. So we have to add some. Oh, this is just wrong, actually. Actually, no, maybe this is right. Maybe that is how I do the modification. You just times W, right? You would only, yeah, for Dijkstra greedy, you would only you would only be on a node once anyway. You would never reverse more than once, and you would never leave from the same place twice. So I think this is fine. Okay, so then now, yeah, I mean that's good. Yeah, okay. If weight is less than best of 3, oops. Yeah, best of 3 is equal to okay, and then heap we best of nope, get away, you noob. Okay, right, and then return -1. Otherwise, if node is equal to n-1, return D. Why am I saying best of node? Whatever. Okay. We have 5 and 3. Hopefully, why does this keep changing on me? I always went in this view. YOLO go. Okay. Yeah, much easier. I mean, it took me 22 minutes to try to figure out that one and 4 minutes on this one. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, take good mental health. I'll see you all later and take care. Bye bye.